This is done by Michalina, Natalie, and Caio. A wave is a disturbance that moves away from wherever it is created. There are two types of waves, that transverse and longitudinal. We will demonstrate this using a slinky by our performer here. In the transfer waves, the disturbance is perpendicular to its direction, like so.
Ready? No, don't go nowhere. For transverse wave. There you go. Good job. Okay.
In longitudinal waves, the disturbance is parallel to its direction, like so. A common misconception about waves is that waves push particles away from the source of the disturbance. In reality, waves are only transfer of energy caused by the disturbance, not the actual particles in the wave. An example of the waves in the ocean is one. When you feel a push by a wave in the ocean, it is not the actual wave that is pushing you. It is just the transfer of energy from the waves to your body. The water particles actually stay in the same general location. The same concept applies to the slinky. If you choose one ring on the slinky and observe it, it always comes back to the same original location.
One very common type of wave is a sound wave. One important characteristic of sound waves is that it travels at different speeds in different mediums. Listen as the pencil is tapped against the steel rail. Now listen as Caio taps his hand on the pencil. As you can see, you can hear soft taps clearly from all the way at the end of the rail. And the reason is that the speed of sound travels at 5,960 meters per second. But if the pencil is tapped on Caio's hand, we can hear very little or almost no sound.
Alright. Well, I'm going to show you guys how to find the speed of sound. Speed of sound is given by VW equals 331 meters per second, which is the speed of sound at sea level at 0 degrees Celsius, multiplied by the square root of the temperature of the air in Kelvin, divided by 273 degrees Kelvin. So, all we gotta do, first of all, the temperature today, by the way, is 17 degrees Celsius. So if we convert that to kelvins, we get 290 Kelvin. So we just plug in our variables. Divided by 273 Kelvin. And we solve for VW, which gives us 341 meters per second. As you can see, speed of sound is faster in warmer temperatures. This is speed of sound for 0 degrees. And we also looked up the speed of sound in the steel rail, which was 5,960 meters per second through steel.
That's pretty fast.
It is pretty fast. As you can see, the speed of sound is much faster through a denser medium, which is why in the demonstration we did outside, we were able to hear the taps of the pencil all the way on the other side of the rail.
two important properties, wavelength and frequency. Wavelength is the distance between two adjacent parts of the wave. For example, in ocean waves, it is the distance from the top of one wave to the top of another wave. And you identify the wavelength with this symbol, lambda. Frequency is the amount of time something vibrates in one sound. And in sound waves, it is perceived by pitch. Pitch, frequency, and wavelength all correlate with each other. Take this ukulele, for example. The different frequencies are created by tightening or loosening the strings, which causes them to vibrate faster or slower. Notice the different pitches. The lowest string is the C string, which has the lowest pitch. The tightest is the A string, which has the highest pitch. If you look closely, you can see that the C string is also thicker than the A string. That is what causes them to have different wavelengths. Thicker strings have greater wavelengths, which means a lower pitch. Thinner strings have smaller wavelengths, which means they have a higher pitch. The relationship between wavelength and frequency is given by VW equals the symbol for wavelength, lambda, which is a symbol for wavelength. The relationship between frequency and wavelength is given by the speed of sound equals frequency times wavelength. We're going to figure out the wavelength of the A string and the C string. So let's go ahead and solve for our variables. Wavelength is equal to the speed of sound over frequency. Earlier, we've already figured out the speed of sound today at 17 degrees Celsius, so we can go ahead and put 341 meters per second divided by the frequency of the A string, which is 440 hertz. So once you do that calculation, you get 0.78 meters. Okay? So now we can go ahead and solve for the C string. Again, let's solve for our variables first. Wavelength equals the speed of sound times the frequency of, divided by the frequency of the C string. So wavelength equals the speed of sound, which is 341 meters per second, over 262 hertz. Once you do that calculation, you'll see that it's 1.30 meters. And if you take a look at this, the C string has a longer wavelength than the A string. So what that tells us is that the longer the wavelength, the lower the sound. See what I did there?
So now I'm going to show you guys how to find the Doppler effect, which in reality is the frequency observed. So the equation is the frequency observed equals frequency of the source, and let's say the frequency of the source was 500 hertz. Times the speed of sound, which we calculated earlier was 341 meters per second, over the speed of sound plus or minus. Now, if the source is coming at you, you're going to use minus. If the source is going away from you, you use plus. So we're going to do it for the source coming towards us. So we're going to do minus, and the speed of the source, let's say I was running at 3 meters per second, which is not very fast at all. But, so we just plug in our variables. frequency of the source, 500. Speed of sound is 341. Divided by 341 minus 3 meters per second. And when you do all the math, it comes out to 504 meters per second, which means that that's the frequency observed by the whoever's standing there when the car passes by. The frequency changes from what the actual frequency is 500, but we observe 504 when it's far away, and that's the Doppler effect. This is a picture of Kingston 9 months ago when he was in Michelina's womb.
One common practical use of sound waves is the use of ultrasound imaging in medicine in order to see inside the human body. Ultra-high frequency sound waves, which are so high that they are not audible by the human ear, are produced by a transducer and transferred by contact into the area of interest, which then bounce back and are picked up by the transducer. An image is formed based on the amount of ultrasound that is absorbed by tissue in the body. An example is the prenatal ultrasound used to see a fetus while it is still in the womb.
I'm filming you.